Morning everyone, welcome to our next lecture, and today the topic is exchange spin waves. In this lecture we will discuss the dispersion law of exchange spin waves. We will go a bit into quantum mechanics spin wave on linear ferromagnetic chain, so principally it's so-called Bloch magnon, and then we will discuss a bit about quasi-particles, magnons, and a few words about magnon relaxation. So you have seen these three pictures in the three dispersion curves for backward volume, forward volume, and magnetostatic surface spin wave in the intro lecture. And in all these cases, we completely ignored exchange interaction. That was just dipolar spin wave, so-called, or proper name is magnetostatic spin wave. And this is a topic of our next lecture. But as soon as you go to larger and larger k, which means that your wavelength is getting shorter and shorter, then angle between two neighboring spins is not zero anymore, and the exchange interaction, which has electric nature, it's part of Coulomb interaction, is waking up, and it's getting stronger, it's dominant. So exchange energy is dominant, and then dispersion goes up simply according to k-square law. So our topic for today is actually, that's what we consider in this lecture, pure exchange waves. I understand that it would be logical to start with this one, but I decided to go first with exchange because here everything is a bit easier in terms of all these formulas and so on, and it will be easier for us to couple both of them, dipolar waves and exchange. You remember this slide, and I said that in this Landau-Lifshitz-Gilbert equation, what we usually do, we put here different fields, effective fields, and this B effective, and among all others there is B exchange. And that's exactly the field which we want to consider now. So what is a field coming from this exchange interaction? So here is the material simply taken from Gurevich-Milkov, and what they say is that the energy of exchange interaction of ferromagnet can be represented in the form of this energy term, U exchange 0, and plus non-uniform term uses exchange delta, which is, this is a static one, and this is a dynamic one. Then what we need to do, so in the, when we discussed Heisenberg exchange model, we considered hydrogen molecules, so two electrons more or less, an exchange between them. But when you come to the real media, real material, it's 3D structure, and there are many neighbors. And strictly speaking, we are not sure if Heisenberg model would work also for 3D case, but in reality, in practice, it does work. And then in this case, this exchange integral can be rewritten in such a form where we have derivative of magnetization in one lattice point, dm over dxp, and then in another neighbor, dm over dxs. And you see here there are this summation, so we take into account three coordinates, x, y, and z. And so that's a full formula, and here we have this QPS, it's exchange interaction, so it's proportional to the exchange integral J, which we considered in Heisenberg model. And what we do afterwards, we just simplify our formula for isotropic ferromagnet. So isotropic means that this one is constant, it's the same, doesn't matter in which direction we go. And what else we do, we principally neglect the static case because we are interested in exchange energy coming particularly from dynamics, from the precession of spin. So when angle between two neighbors is not zero anymore, and that increases energy, and that's what is of interest for us. Therefore, we can rewrite this energy here, exchange with delta, as Q Laplace operator M large. where m is our magnetization. And this Laplace is very important because at the end of the day it gives us k-squared dispersion curve. Yeah, so principally this one, okay, that's already next step to go to truly AC part. We again can split this one. There's also some static component, but in order to switch completely to dynamic component, we write H small exchange, which is rewritten again in this Laplace, but here you see we don't have any more m, which is taken into account. You remember when we were discussing polar tensor, we described m as m0 plus m small. So this part with m0 we remove, and then we focused only on m small, which is a dynamic component perpendicular to the m0 magnetization. So what we see here, we see this Q, which is named exchange constant sometimes, non-uniform exchange constants, or constant of spin stiffness. But in literature, you will find many other constants. In particular, Gurevich-Milkova attracts our attention to eta and to d. All of them are exchange constants in some sense. If you want to have a better coupling to the Heisenberg model, which we described with this yacht exchange integral, then I place you this formula, which is more general, where we have z, which is a number of nearest neighbors. We have here r, which is nearest neighbor distance, and so on. So if you are interested, and so it's more or less more detailed representation of the same. I give it to you just for case you are curious, but in practice, usually we don't go start from the very basics, from real atom physics. Instead, we just use one of the exchange constants, and then there are different methods how you can measure it in your experiment, and just to double check to get value for Q, for example. Good, so this is our field, and now I have a special slide where I try to collect different exchange constants, because if you will go to literature, you can be lost. There are really many of them. At some point, I asked my doctor supervisor, Professor Milkov, why there are so many exchange constants. And he made a joke that probably every new scientist thought that he can invent a better one. But my message is that just be careful. So nowadays, what we are using mainly is this exchange constant A, or exchange stiffness lambda, which is 2A divided by mu0 ms. Yeah, here there is a values also some that it's easier for you to understand, and also units. So I show them for YIG in SI and CGS system. So we have A, we have lambda. Be always careful. Yeah, for example, for spin wave dispersion, actually exchange stiffness pretty often is more important. That's why if you want to have stronger in contribution of exchange energy to your system, like we did it in gallium doped YIG, you not necessarily have to search for a way to increase your A, but instead, if you will decrease MS, simply saturation magnetization, your dispersion curves are getting much more exchange, and that's what really happens. Therefore, keep in mind that that simply MS is very important for properties of exchange waves and for interplay between dipolar and exchange energies. So, other constant D, 2A over MS, alpha exchange also will be used. So, in my lecture today, I will use different sources. So, some of them will be used eta, Q, and lambda exchange, but this is not this lambda exchange. That's a different one, because this one is named exchange length. Exchange length, it's a parameter which is also very important. It more or less gives you a feeling on which distance exchange interaction acts. So yttrium iron garnet has a very huge lattice constant, 1.2 nanometer, and exchange again, you can find formulas where it will be 2 pi smaller, pi smaller. But we believe the most correct is this one, so around 16 nanometers. And that's a distance which you have to keep in mind when you want to describe exchange spin waves. It's also important for micromagnetic simulation. Strictly speaking, when you want to do proper micromagnetics, your unit cell should not be larger or shouldn't be much larger than exchange length. Is it correct, Andrii? Good. Andrii is our expert. He is trained by Dieter Zeus and Klaus Albert. He knows. Good. Yeah, so here you see some values in SI and CGS values also here. I hope this simply collection will help you, but still don't hesitate to double check everything carefully because sometimes it's a bit messy in the literature. Good. Now let us try to get dispersion curve for spin waves. So dispersion means we need to find a frequency as a function of wave number, and to do it, of course, the easiest way we use ansatz for plane wave. So simply M is described as minus IKR. So we did it already in polar tensor, but that was just oscillation. So here was staying I omega t. But now we are bringing coordinate in the system. And this is a plane wave, IKR. And then when you will plug it simply in this Laplace operator, if you define your exchange tensor, you will immediately get this alpha exchange k squared m, or written like this in CGS system. So we have now value how field, external field or magnetization, the couple depends on the k squared. And then what you can do again, like we did with damping, we don't want to solve Landau-Lifshitz from the beginning, don't want to get polar tensor. Instead, what you can do, you can replace now our resonance frequency omega h with omega h plus alpha exchange k square. And then if you plug in this substitution, you will immediately get, you principally already see it here, that resonance frequency is dependent on wave number k, but to do it properly, you need at the end of the day to get your permeability mu, which we had in the previous lecture. And now this permeability depends for symmetric anti-symmetric constant component of the tensor. So this mu is tensor, as we remember. And now it depends on omega h, means magnetic field h is sitting in here. And it depends on k next to exchange constant, and omega is applied frequency more or less. So it's a frequency of our applied external field. If you want to get a dispersion relation, it's not sufficient because you need to take into account that angle matters. So now what is important is angle between the magnetization, M0, and direction in which wave is propagating. And we don't consider here shape anisotropy, so it's infinite or crystallographic anisotropy. It's infinite media. Therefore, only one angle matters between M and K. And if you want to get a dispersion, principally, you need to use this formula from electrodynamics, which says that permeability divided by permeability parallel should be given by cotangents squared of theta k. And if our ferromagnet is saturated, this mu parallel can be taken as 1. Then you just take this mu, which is more or less this one, make it equal to cotangent square of theta. And from there, you just need, at the end of the day, you need to define omega as a function of k. And that's the dispersion which you can get for exchange waves. So it's written omega h, omega m. Omega m, so magnetization is sitting here, multiplied alpha exchange. So here again, k squared. Or pretty often people rewrite it in terms of this ak large square minus bk squared. Just historically, somebody presented it like this. But principally, it's analytical solutions, very cool. So we have analytical solution for purely exchange wave. And now our job is to analyze these dispersions. Other questions? No. All good. So, that's our formula. And of course, what we want to know, we want to understand where our dispersion starts. So we just shift k to 0. And you see that it depends now for the angle theta k. If theta k is equal to 0, then omega, well, then this part is 0, this 0, 0, then omega is simply omega h. Yeah, so here's tan square, omega h, so it disappears. It's easy. If we have theta k equal pi over 2, then this part will give us 1. And in this case, omega will start from this value, omega h plus omega m, which we already know, omega perpendicular, and this is ferromagnetic resonance frequency for in-plane magnetized film. What happens if k goes to infinity? If k goes to infinity, then principally this term disappears. This term also is much smaller than this one. And finally, we are coming to the original dispersion of exchange spin wave defined by Bloch, where we see that omega is proportional to k square, and there is no angle inside. That's why if you've majority of people who studied spin waves in basic course, the solid state, so they say that exchange spin waves are isotropic. So it means that we have magnetization, doesn't matter in which direction it propagates, it's isotropic, and this is correct. That's exactly what you see here. So there is no angle, but in reality, in practice, there is always additional contribution from this shift here up. It's taking place of these components here. These are still from dipole contribution, so principal from the energy. So it means that, strictly speaking, they are isotropic, but in reality, as long as you don't work with very large k, you need to take into account contribution from dipolar fields, and they are anisotropic. They are not isotropic. Yeah? Therefore, exchange spin waves are isotropic for large k only. Just keep in mind. How does it look for k with which we are working in our experiments? This is a dispersion, as we said. When theta k is equal 0, it goes down to omega h. Yeah. When theta k is pi over 2, then it goes here. And then they go up, and the larger k you go, the higher frequency it is, the closer is as these two lines are. And at some point, they will merge into one line. This one, where angle is not. That's how dispersion looks for exchange spin waves. And please keep in mind that this is not only two dispersion lines. When we were discussing, or we will discuss next lecture, magnetostatic waves, one line means one dispersion. Here it's a different picture. Here it means that all this is a band. So what is shown here, it's a top band and bottom part of the band where exchange spin wave exists. But in each part of this band, you have different angles. So this is theta k, which runs along magnetization, and this one which runs perpendicular to magnetization. But in between, you have dispersions for all other waves, which have some other dispersions. Good. Then let us analyze group and phase velocities. For data processing, for example, it's very important how behaves our velocity with increasing k. Why do we need increase in k? Simply because short wavelengths is getting shorter and shorter, and it's better. So you come in closer to CMOS for data processing. The smaller wavelengths, the better. And for example, another object under investigation, plasmon polaritons, they also can have nanometer wavelengths, but they have such situations that when you bring wavelengths to nanometer scale, dispersion is getting flat. And flat dispersion means zero velocity. So it means that you do have plasmon polaritons, but they don't propagate. They cannot carry energy. And in this case, spin waves are much nicer, because what you can do for us group velocity, so let's say if you analyze phase velocity, it's simply omega over k, as we discussed. Then you have two terms, omega h divided by k, and another term, it's proportional to k. Of course, if you go to higher k, this term will disappear, and you see that phase velocity is getting proportional to k. But phase velocity, it has, it's usually less critical, at least in terms of carrying information. For us, what matters is group velocity. And this one is found as d omega over dk. And of course, if your dispersion is quadratic, then you will get situations that group velocity is proportional to k, is inversely proportional to lambda. So it means that the shorter the wavelengths you have, the faster your spin wave is, the better it is for data processing. That's why now a lot of efforts are going on to get shorter and shorter spin waves. So principally, people reached already 50 nanometers in different materials. And they use different tricky physics how to get them. Pretty often you need Bessey synchrotron in order to measure your spin waves with X-rays, because such short wavelengths it's hard to see. But trend is clear that people want to go towards shorter and shorter wavelengths. Yeah, and this actually picture underlines this very nicely. So here it's a very simple dispersion curve calculated, taking into account both dipolar and exchange energies. But this exchange part here is more or less. So if you will use this formula, which we obtained, it will be very close. Yeah, so it was used, calculated using Simple-Kolikov-Slavin approach, which takes into account both waves. And what is plotted here is dispersion frequency versus wave number, but in log-log scale. So you see here's logarithm. And I go down to 5 nanometer wavelengths. So here's this blue, it's just wavelengths, just to give us some values. Why 5 nanometer? Because I will show you soon that if you want to describe spin wave dispersion in the whole Brillouin zone, edge of Brillouin zone is given simply by pi over A, where A is a lattice constant, then your dispersion won't be quadratic, it will be cosine. And it means that you can use all this formula only, let's say, in half, maybe first half of Brillouin zone, or even less. That's why for us it means that wavelengths will be 1.2 nanometer, like lattice constant. Yes, that's why I stack here that 5 nanometer just to be able to use this formula. I don't go further, but already even at this wavelengths in YIG, the frequency will be 2 terahertz. So it means that we're already very high in frequency, and it's already interesting. So we kind of can have a good overview. So this is a dipolar part. You see it's practically flat on this scale, and this is exchange part. So here, this one shows us a group velocity in kilometer per second. And you see that it's quite small, then it's even negative, because we calculated here backward volume waves, which have negative velocity. Then it goes to 0 in this minimum of dispersion, and afterwards it starts to increase. The increase is linear, as we discussed. It doesn't look linear because of logarithmic scale, simply. But it's clearly visible that we can go, for example, up to 22 kilometers per second as fast spin waves. Lifetime behaves differently. Lifetime first is practically constant because frequency practically constant, but then it decreases. Why it decreases? Because our lifetime is inversely proportional to frequency. So it means if you go to larger and larger k, frequency increases, lifetime should drop down. Therefore, our waves are getting faster, but they are dying also faster. So lifetime here at the end is around 1 nanosecond. So it's not bad if you will manage to process data within 1 nanosecond. But for practice, of course, it's an issue we need to take into account. Next term, which is important, is free path, which is nothing else as a group velocity. So this curve multiplied with a lifetime with this curve. And here what we have, group velocity is proportional to k, but lifetime is inversely proportional to omega, and omega is proportional to k squared. So it means that our free path is inversely proportional in this very simplest estimation to k. How does it look like? So this red curve describes our free path, And principally here in dipolar region, these formulas are not applicable. Therefore, this part we just skip. Then there will be a point where free path is 0 because simply group velocity is 0. But that is a part which is of interest for us. So still there will be some contribution from exchange, from dipolar contribution, but this part already decrease of free path proportional with k. Here is our exchange wave. So it means that our spin wave will propagate smaller and smaller distance with increase in the wave number. And nevertheless, there will be a nice optimum, 110 nanometer for the YIG. And here the free path will be around 200 micrometer, which is a lot. It's more than enough for your structure. Usually your device is, I don't know, a few micrometers length, so 10 microns. But principally, if you work with this wavelengths, then it's very good. This wavelength is possible to excite. You need to create a microstrip antenna, for example, to send current, and the width of your antenna should be smaller. Nowadays, we can do 50 nanometers. Again, Andrii can do that. And in Brno, in SciTech. But detect them is problem. We need to either to use the same antenna or synchrotron or search for some other tricks because it's beyond optical limit. And if you want to use brilliant light scattering spectroscopy, which we will discuss in next lectures, it's blind to this wavelength. So we have issues how to detect this short wavelengths. Yeah? So we have a lot of techniques to work with these waves, but here it's already not so easy. But coming back to general issues, so you see that it's maximum, then it drops down to 16 micron, which is still good. And final parameter shown here, it's a ratio free path divided by wavelength. So principally, it's a nice value to describe damping. So how many wavelengths it propagates before it decays. And in this case, we are in quite good situation with exchange waves because, again, for dipolar waves, story is different, more complicated. But for exchange waves, you see that principally it should come to a constant which depends on alpha, on Gilbert damping parameter. And for this thin YIG of YIG, thin films of YIG, it should come to 3000 or so, theoretically. And it's constant. So it means principally starting from this point, you have a very comfortable situation that wave propagates like 1,000 periods. It's probably comparable also to photonics in photonic crystalline silicon. So, of course, we cannot compare with photonics when we watch into stars, but in some chips, maybe it's already quite good. Therefore, one of the ways, because damping is one of the issues, obstacles behind magnonics, and one of the 8 ways to minimize this role is to go to exchange waves with the short wavelengths. Good. Other questions to this part? No. Today everything is clear. Good. Okay, so now let us go through a bit of quantum mechanics. So this part is taken from Stancil Prabhakar book. And first, we need to understand what Bloch magnon is. Imagine we have linear chain of spins, like it's shown here, and we apply magnetic field in that direction, so they are all magnetized in this direction. Then what we will get magnetization, which is more or less sum of all these magnetic moments divided by the length, yeah, if it's 1D. And that's what you see here. It's named Bloch magnon. It means it's just a flip of a single magnon, and then we will get decrease in magnetization, delta M, by the value principally to magneton Bohr. Because if you have this chain, each of these spins have magnetic moment mu B, and when you take it out of the system, it will be decrease in delta M by mu B. But when you add it back, but with opposite sign, it means it will be 2 mu B, magneton Bohr. And this is named Bloch magnon. Pretty often, especially in quantum mechanics, that's exactly what is used. But in reality, this configuration will not give you the smallest energy in the system. The point is that energy here, exchange interaction, so if our yacht exchange integral is positive, will be huge. So by this flip of single spin, you will significantly increase exchange energy, and it's kind of not really the way how system prefers to have it. Therefore, what happens in reality is that all spins will slightly be tilted, like it's shown here, and the tilted angle will be as large that each of them slightly decreases its magnetization, but in a way that when you will summarize a projection of all these amps here to this original axis, the difference in magnetization will be exactly the same like in previous. So 2 magneton Bohr. And that's how and you see that as opposite to the previous case, it was not really collective excitation. It was just a flip of single spin. And this is a collective object. That's kind of proper magnon, how we refer to it. The last what we have to keep in mind, of course, that this delta, that magnetization cannot stay like this, yeah, because we have Landau-Lifshitz equation. It means that as long as you have some angle, there should be precession. So there will be magnetization precession, and that's the magnon how we describe it. Good. Other questions to this? Now we need to come to Heisenberg Hamiltonian. Yeah, as I said, many phenomena can be described by Heisenberg Hamiltonian, even if it's not one-dimensional chain where you have only one neighbor, two neighbors, but in 3D structures. Therefore, we still can use this model. So we have here two, we have exchange integral, and n helps us to find a sum for Hamiltonian for energies for all neighbors. So you always take n and n plus 1, so you take into account neighbors. And for further, we simplify our life a bit when we take into account that spin is equal 1/2, so it's a spin of electron, and J is positive, so we are describing ferromagnetic structure. What you can get in this case, so in Stanzel you can see how they derive it, but I think for quantum physics it's something very well known, that this Hamiltonian can be rewritten using Pauli spin exchange operator. This P, so you see it has another form, it's 2p and n plus 1 minus 1, so that's how our Hamiltonian looks like. And P is just the operator which replaces positions of our spin. So if you have P high up and down, so this spin was up and this one down, then when you act with operator P on it, you exchange them. So first you have spin down and then you have spin up. So you kind of, you do this trick. And yeah, here just great text also copy pasted from Stanzel to refresh your memories. What is bra and cat? Yeah, so bra means complex conjugated, a state of a wave function. Cat means just a state of wave function. If you have some continuous variation of your wave function, that when you have this situation, you need to take integral psi, complex conjugated psi, and then over volume. And if it's two different wave functions, then it's probability amplitude of transition between one state to another, and you can find it also through this integral. So that's methodology, how we work with it. But we are coming back to our Hamiltonian, written in this Pauli operator. And now let us define a ground state. So G means smallest energy, our ground state. And of course, ground state in this case means that all spins are parallel, that energy is smallest. No exchange interaction, so exchange interaction is happy and principally is equals 0. So how to get this value, more or less energy for, so how to define this operator, this part, which is more or less probability, yes, so that our system is in ground state, or energy that when our system is in ground state. What will happen in this case if you replace one spin with another, since all of them are parallel, this operator P will be equal 1, and nothing changes. And then you have here 2 minus 1, so there will be 1. And more or less this n, you just go from 1 to n capital and large, which is number of your spins. Therefore, you can immediately get this value for the ground state minus j n over 2. Next little step we do, just to simplify everything a bit, you see that you have this 2 which you can put inside of your sum, then here P will disappear and there will be minus 1 over 2. But we can do remove offset. So it's not a problem in all this business to shift offset up or down. And if you will write here instead of minus 1 over 2 minus 1, then you are in perfect situation since your ground state will have 0 energy. So again, as I said, when you have ground state, you exchange 2 spins, you will get 1 here and then Hamiltonian, so energy in the ground state is equal 0, which is exactly what we need. And then by flip of spin, we will shift energy up. Good. What will be the lowest excited state? When one spin is flipped. And let us try to describe it. So there are some mathematical steps so described in stencil. And yeah, but the idea is clear. Yeah? If you have more than one flipped spin, then energy, of course, will be higher. So we need principally to describe only Bloch magnon. And what we need to do in this case, that the actual state of the system psi can be expressed as a sum of all possible states with one flipped spin. That's why we need this sum m. And you summarize all states m, but you multiply it by this part m Brian cat psi, where this part m psi is equal is a probability amplitude that the spin is in the state with a flipped spin at location m. So principally it shows that particularly at this state spin m spin is flipped. So this formula can be shown if you will reproduce it in terms of vectors. It's very general. You can write it like this. Next. Next, we are coming to Schrödinger equation. Hamiltonian acting on our state psi will give us energy times psi. Everybody knows this, very simple step. Second, what we do, we add this bra n on the left and right side of the equation, and then we will get n Hamiltonian psi and psi. Next step, we use this property and we just replace this psi with this part. And then what happens, we have n Hamiltonian m psi, and here we still have the same factor. Next step, Hamiltonian, we just use the one we obtained. It's this Hamiltonian with offset introduced, and that's what we will have here because we have already one summation which comes from this part when we checked all spins and checked which of them is flipped, and now we have another sum I which is coming from Hamiltonian itself, and we've got such a nice formula which more or less describes our single lowest excited state. Now our task is to start to simplify it. So how do we simplify it? So first of all, what we we need to consider the following. So if neither I on nor I plus I are equal to m, then two parallel spins are flipped, leaving the state unchanged. So it means that if you are staying, so our chain, only one spin is flipped. If you are staying away from this point, because what we are doing now, we exchange spins. If you will exchange this two or this two, nothing will happen. Therefore, this component, as we said, p will be equal 1, therefore this part will be equal 0. So it means that we need to take into account from all the sum, we need to take into account only the situation when our spin is located at m, and then what will happen that m will change its sign, but also m plus 1 will change its sign. Yeah, so if you will flip this one, if you will exchange this two, then this will be spin down and this one will be spin up. So we need to take into account these two guys. So then this part will be equal m plus 1 will be this state m plus 1 minus m. And the same happens if you exchange this to spin up and spin down. But in this case, you need to take into account m minus 1 minus m. And it means that this part can be then simplified. You don't have any more p as this operator, but instead we have the sum over m, only one sum left. Then we will have n, m plus 1 minus m, m minus 1 minus m. And then we have this probability amplitude, and here's the in our energy times n phi. Psi. Good. Next point is that in principle, that state with a spin flipped at location m is orthogonal to the state with a flipped spin at location n. So it means that it's, if you will the easiest way to look on that in the point of view just of geometry. So if these guys are describing more or less vectors, then you always work in orthogonal planes, and flip in one plane doesn't change much in another. Therefore, what we can get rid of this second sum, since for us it's important only the case when m is equal n. And that's why we can use Kronecker delta and define it that m psi is equal delta mn. Yeah, and then what will happen, here's written just for the very first term, for this one only, so this are coming in the same manner. So then this term m plus 1 m psi can be rewritten as delta n m plus 1 m psi. And you see here we have m. Therefore, we want principally to have also m here. You can understand it that we simply rewrite. We introduced another n. So we shifted both of them by 1 to the left. So here we will have m, then here we will have n minus 1. And that's why at the very end you will have such j n minus 1 psi. Simplifying the remaining terms, so principally the same you do for other terms, like it's shown here. And at the end of the day, you will have n minus 1, n plus 1, and 2 times n psi, like it's shown here, psi, and energy. And the very last step, what we need to do is we need to come to real coordinates. So at the moment we were discussing, there was a chain, and we were talking about number. Yeah, so what is the number of our spin, which we flip, or number of spins which we exchange. And now we want to bring it to coordinate. And for this we say that simply there is a xn, and now n defines which of the spins we are talking about. And they are displaced by a, where a is a lattice constant. So it means that you just go, yeah, just a. It's clear like it is in the crystal, but here it's 1D case. Okay, and then we introduce the Cn, which is a probability amplitude that your flip spin is actually allocated at the position n. That's what we have here. And it's clear that n psi can be rewritten as Cxn. This one can be rewritten plus minus a when it's shifted to the left or right. We just now come into a coordinate. We plug everything into our equation, and we are coming to this simplified equation which we need to solve. And to solve, finally, we again use approach ansatz for plane wave, which is shown here. Exponenta EK xn. We just put it inside of our formula, and we will have xn minus a, xn plus a, and so on. Then simplest mathematics, and we will come to the very important formula that energy is equal to yot 1 minus cosine k a, where a is a lattice constant. These two exponents will give you cosine, and if you take into account that energy is nothing else as h omega, you can finally get this dispersion relation for exchange wave in the chain, which is equal to yot over h 1 minus cosinus Ka. And that's exactly what I said, that if you plot dispersion curve for exchange waves, remember in the past we said that if your wavelength is very large, very short, k is very large, then dispersion, it's not anymore dispersion for dipolar waves, it will become parabolic. So it's getting k squared dispersion for exchange waves. But now we went through the whole brilliant zone and we say that no, it's in reality it's cosine, but only at the small k it's k square. So just keep in mind that you always need to understand where you work. So in majority of the cases in Magnonics we are working here close to 0 point, but we need to know that there are magnons with short and shorter k. And as I said, in this picture, in this graph where I analyzed why spin waves are good or bad for data processing, yeah, especially was if this corresponds to 1.2 nanometer lattice constant, so we stuck to 5 nanometers, so we were somewhere here. So that was a part we analyzed in that graph. Good, so we have dispersion curve. Again, as I said, if you use approximation that Ka is much smaller than 1, then we will get our parabolic dispersion, k squared. And also what you can see in the stencil Prabhakar is that simply by comparing this omega with a value where you just take momentum, yeah, h squared k squared divided by 2m star means effective mass of magnon. Simply by comparison these two formulas, you can then immediately get a value for effective mass, and you see that effective mass of magnons depends on exchange constant and on the lattice constant, exchange integral yot, and on the lattice constant a. In a few slides I will show you another way how you can define mass of magnon, but here it really comes from down to the atomic scale. Other questions to this exchange part? Okay. Good. So then we have the dispersions. Now let us come back to the practical side. YIG. Who knows why YIG has such small damping?
YIG has a very low spin-over coupling, and therefore and is an isolator with a huge bandgap. So the magnons have no mechanism to give energy away to the phonon or electron system.
Yeah, correct. I see that you're working with YIG for a long time already. That's good. So let me now tell in more details what Rusty just said. His answer was absolutely right. So what is yttrium iron garnet? Its artificial garnet was synthesized 60 years ago in France for the first time, and to the best of my knowledge, it still is a champion in terms of damping. It's a material with the smallest damping, which is very attractive till now, and it's used in many different approaches, so in quantum magnonics, for RF applications, and for many other approaches, particularly YIG is of use. We also use it in our group. So, what is YIG? It's yttrium, iron, garnet. Chemical formula yttrium 3, iron 5, oxygen 12. Or sometimes people rewrite it in terms of ions. Yttrium 3 plus 3, iron 3 plus 2, iron 3 plus 3, oxygen 12 minus 2. It's very complicated structure. So if you speak about a primitive cell, at this part, then we have 80 atoms. If we speak about unit cell, we have 160 atoms in it. So it's very complicated structure. Lattice constants of space from here to here is 1.24 nanometers. And cubic structure. So why did we split it into two parts, these ions, iron 3 plus and iron 2 and 3 ions? Because these ion atoms, this yellow, they can sit in different sides of the crystallographic structure. So some of them are in octahedral site and some of them are in tetrahedral site. And in this case, we don't have direct Heisenberg exchange, but the magnetic moments between them is coupled through oxygen atoms. And there is such phenomena as super exchange, which we didn't discuss here. So for people on YouTube, you can find, I think there is a brief description what is super exchange, or read it in Krishnan, for example, or any other book. And super exchange, it's known that it couples our sublattices of material antiparallel. So it means that it principally, this oxygen ensures that magnetic moment here and here are pointing in the opposite direction. And why is it important? Because if you will take one chemical formula, that you have iron, five ions of iron, 2 of them will be pointing in one direction, and 3 of them will be pointing in another direction. So you have the situation. So it means that magnetic moments from these 2 are compensated, and only one iron 3 plus gives you magnetic moment. Therefore, YIG is ferrmagnet, so it's uncompensated ferromagnet. It's ferrite, which means that it's magnetic dielectric, and it has very small magnetization, because majority of magnetic moments coming from this iron is compensated, and only 1 out of 5 is really give you magnetization in this material. So now coming back to the question of damping, why it's small. As Rostislav said, there are 2 physical mechanisms. First of all, in metallic magnets, spin wave damping is usually 100 times higher immediately, simply because there are free electrons. So there are damping mechanisms associated with free electrons, and in YIG there is big energy gap. Yes, so this is very good isolator. There are no free electrons, so there is no problem. Second question is how energy from our magnetization precession goes to phonons. As we discussed, it goes through spin-orbit interaction. So we need to look what is a spin-orbit interaction. And in the previous formal slides, we have discussed that energy of spin-orbit interaction is S proportional to S times L, orbital momentum. Let us have a look what is S, but capital S. In this case, for iron 3 plus ion. So we just fill it according to Hund's rule. So we fill all these orbitals completely, and this orbital will be exactly half filled, and atoms will go to all these other orbitals, because simply to minimize Coulomb energy, according to Hund's rule. Therefore, if you want to calculate how much is your S large, you just need to summarize. So each of them gives you 1 over 2, and there are 5 times. There are 5 over 2 spins. So like Planck constant. Let us have a look on the L. L, according to Hund's rule, it's less than half full. It's gonna be L minus, that's total angular momentum. Let's first look L large, orbital momentum. And you know that this one has +2, +1, 0, -1, -2. Therefore, when you will summarize all of them, the angular momentum, orbital momentum will be equal to 0. And this particularly the reason why spin-orbit interaction is suppressed in the I would not say that it doesn't exist in reality, because otherwise we would have no damping probably. But it's very small spin-orbit interaction, and as a result, the coupling of spin system to vibrations of lattice is small, and as a result, damping is small, simply because it's L equals 0. Yeah, then you need third Hund's rule just to calculate yacht total angular momentum, but since L is equal 0, it's easy. It will be simply equal to S. And why we need it? Because we can calculate magnetization for yttrium iron garnet. Very simple. We need, simply based on these rules. So what you see here, it's very complicated, but for us it's important to understand that this one cube here, it's one chemical formula with 5 iron atoms inside. Then you can define primitive cell, which will be 4 such formulas. And if you want to define a unit cell, then there will be 8 of chemical formulas, like it's shown here. Yeah? So this is always unit cell, but for us, we just focus now on primitive cell. So how much magnetic moments do we have in one primitive cell? You remember, so in each of them is 5, but so now we kind of take chemical formula, but multiply it with 4. So it means we will have 12 momentum point, 12 iron 3 plus spins pointing in one direction and 8 in the opposite direction. So it means for one primitive cell, we will have 4 only magnetic moments. From each iron 3 plus ion. So, and each this ion gives us 5/2, spin is 5/2, but each 1/2 gives us 1 magneton Bohr. Yeah, so spin 1/2 gives us 1 magneton Bohr. So it means that we have 5 times magneton Bohr in one chemical formula, and now we need just to multiply it by 4, and it means that in one primitive cell we have magnetic moment coming from 20 magneton Bohr. And the next step, that's a very nice example because you can really calculate saturation magnetization on your own if you work with isolator. Yeah, so it doesn't work for metals. And the last one, you just need to take this total magnetic moment for primitive cell, 20 magneton Bohr. You need just to divide it by the volume of primitive cell. So lattice constant is 124, it's like this. So this one is A/2 cube. So here staying more or less a volume of one chemical formula. And then we have 4 of them in primitive cell, and you just calculate. And at the end of the day, you will get in CGS 195 MU per centimeter cubic. So in such a very simple case, you can get saturation magnetization for yttrium iron garnet. And if you will go to the laboratory, we'll perform ferromagnetic resonance, we'll measure MS, and the value will be different. Why? Let's say you will go to standard room temperature ferromagnetic setup.
We don't have iron temperature.
Yeah, exactly. Thank you. Yeah, so the reason is that all this is, of course, calculated when we take into account that there is no KBT, there is no chaos. The magnetization is as large as possible, and this you have for temperature equals 0. So this you can get if you measure in our cryo lab. And we really have this value. So David has measured, Rusty has measured, and there is a good agreement with experiment. As soon as you go to temperatures already at 2 Kelvin, you can get it, I think. SPPMS. Good. Very last slide about yttrium iron garnet. I told you that we usually work with very small wavelengths. but in reality, there are many magnon bands, and this is, for example, neutron scattering, if I remember right, and this is some recent results about numerical simulation, how spin waves are calculated in YIG, since it's very complicated material, how it's calculated for also higher mode. So for us, usually when we just work with spin waves, we more or less cut in magnetic moment out of the only this uncompensated iron 3+ moments, magnetic moments. But if you go to larger and larger energies, there might be more complicated modes in between these all magnetic moments, which you have in your yttrium iron garnet. Therefore, there are higher modes, and just keep in mind that they exist there. But what's important for us to understand what is the frequency at the edge of brilliant zone for yttrium iron garnet, and as you can see in this picture, it's around 7 terahertz. So it means that you can work with spin wave in yttrium iron garnet from the frequencies starting from sub-gigahertz up to 7 terahertz if you want to work with the lowest mode. Yeah, but theoretically there are other modes, but that's more complicated. Okay, magnons and magnon relaxation. What is magnon? Magnon is a quasi-particle of a spin wave. So we know that for light we have quasi-particles photon, for sound quasi-particles phonon, and there are many other quasi-particles, excitons, plasmon, polaritons, and so on and so on. And our quasi-particles is magnon. Of course, magnon has energy like any other magnon, a quasi-particle, so H omega. You can find it simply from frequency, quasi-momentum, Hk, and it has mass. How you can find mass? For example, you write this energy in this formula you know very well from quantum mechanics in terms of, and it's just kinetic energy written through momentum k square over 2m. And on the right side of this, you can rewrite this energy as H omega, which is clear, and instead of omega, you can place our dispersion curve for exchange waves. Just you remember for large k, when we have simple parabola, you can plug it in, and then simply comparing this part with this one, you can find a value for mass, and when which depends on so Planck constant, magnetization. So this is omega m depends on magnetization, and exchange constant. So exchange constant is critical. Then, for example, these values are used for yttrium iron garnet for material which we use often. And you see this is a mass of electrons, 6 × 10⁻30 kilogram. And if you want to get a feeling if it's a lot or not, really you compare it with the mass of electron, which we know is a real particle, but very light one. And the difference is around 6.6. So let's say our magnon is almost 7 times heavier than electrons for this material. So it means that spin waves, so magnons are quite light quasi-particles. Spin of magnon is 1. So and this is very typical, you know, so usually real particles like electrons are fermions, and so the spin is not integer. And magnons, like majority of quasi-particles like phonons, photons, and so on, is a bosonic quasi-particle, S equal 1. So principally, you could watch on it a bit from the side that spin is 1/2, yeah, and then when you flip it, it's -1/2. And when you subtract one from another, then you will get difference as spin 1. So then you will have S equal 1. So magnetic moment associated with magnon, it can be found like this. So that is just coordinate vectors. This is ferromagnetic ratio Planck constant. You can rewrite it via G factorial and then, and you will see that principally it's close to 2 magneton Bohr. So also please don't mix up that if magnetic moment associated with single spin is magneton Bohr, magnetic moment associated with the flip of spin is 2 magneton Bohr. Yeah? So if you would remove one atom here, one electron out of the chain, you would change magnetization by magneton Bohr. But when you place it back with opposite signs, then you kind of add additional magneton Bohr. And that's what you see here in this tool. Magnetization, how magnetization change. So excitation of magnon, as we started in this animation, changes magnetization. And to find the difference, M0 is a steady state, ground state when all spins are oriented in the second direction. MZ, it's our state when we do have some excited magnons in the system. And then to find out what is a change in the magnetization of your system between steady state, ground state, and excited state, is simply you need to introduce a number of magnons here, n, and each of them changes magnetization by this gamma h value. So I think it's straightforward. Magnon, since it's boson, if you want to describe its statistic, you need to use Bose-Einstein statistic. Formula is similar to Fermi-Dirac distribution, but here we have -1. So it means that if this exponent gives you 1, you will get a infinite population of magnons, which is a signature for Bose-Einstein condensation. So that's actually at room temperature what we do a lot. So there is a large field in Kaiserslautern, Burkhard Hillebrand is intensively investigating, Alexander Sergei Democrito and Münster, and many other people investigate Bose-Einstein condensation. And what is special about magnons and Bose-Einstein condensation is that usually people, in order to reach condensation of some ultra-cold atoms or so, they decrease this temperature. So you need to go to small t. And with magnons, there are many mechanisms how you can increase this chemical potential mu. And principally, you can bring it to the lowest energy state, magnon state, you have this E energy. And what happens then, you will see that if mu is equal energy, then this part will give you 1, and it means that population goes to infinity. So it means that there are many different mechanisms how you can inject many magnons in your system, even staying at room temperature. You don't have to go to low temperature. And at some point, you will reach a threshold, and we, in our experiment, see a huge signal at the bottom of spectrum. So it means that magnons, when you populate them all over the volume of your magnetic sample, at some moment they get in jump into the lowest state. And this is described as Bose-Einstein condensation. Of course, there are discussions if it's really Bose-Einstein condensation or it's more relay condensation, but what is really truth, what I saw many times in many different experiments, that really if you inject many magnets at some point, there will be some condensation at the lowest state. Why also statistic is important for us is in the view of quantum magnonics. So this is growing field now. Many people are going there, very interested. And why is it important? Because what we want to do in quantum magnonics, we want to work with entangled magnons and then to investigate this Schrödinger physics or Zeilinger physics nowadays, one can also say. So more or less like teleportation and entanglement of different particles. And when you take your magnetic sample at room temperature, you want to measure here, you will have 10 to the power 18, if I remember correct, magnons per cubic centimeter. So you have huge amount of thermal magnons. On the next slide, I will show you what is that. So there are many parasitic magnons. And if you will inject now 2 entangled magnons, there you see nothing. And therefore, what you want to do, you want to have a clean system. That's why you need to go to low temperature in order to get rid of so-called thermal magnons. And then if your system is empty, you can inject as many as you want entangled magnons. You should be able, if you have good single magnon source and detector, which is just in the process, we're just working on that direction. There are pioneer works of Nakamura where he coupled standing magnon in a sphere with qubit. But it's kind of to my understanding, it's a beginning of the path. But if you have single magnon source and so on detector, then you can get kind of you can use this fancy physics, entanglement physics from your magnons. And the question is which temperature we have to go to. Yeah, and this is exactly what Bose-Einstein statistics tells you. So this is density of magnons, or you can say what is the probability that some state with energy E will be populated. And if you will take it for 10 gigahertz and for chemical potential mu0, so what means chemical potential 0? It means that your system is staying in equilibrium. So in any body you have phonons. As soon as temperature is non-zero, there are phonons. And you can increase temperature, for example, it works like injection of many phonons. Or you can excite magnons, and then there will be mu will be non-zero because you have more magnons compared to phonons. But if you wait a bit, there will be equilibrium between phononic and magnonic system. If you are staying in equilibrium, mu is equal 0. So if you take then mu0 and magnons just as an example, 10 gigahertz, here you can see it very well, but even for 1 Kelvin, you will have some probability close to 1 that you will have populated magnons. So it means that even at 1 Kelvin, you will have many thermal magnons. If you go to 100 millikelvin, the probability will be 10 to the power minus 3. So it's already good. So principally, the system is already quite clean. At 100 millikelvin, you should be able to do quantum magnonics. If you go to 10 millikelvin, that's what people are doing nowadays. So there are industrially available cryostats from Blue Force or Oxford Instruments, and then you go to 10 to the minus 20, the probability. That's why we need the system for quantum magnonics. Low temperature should be reached, and this you can get simply from Bose-Einstein statistics. I mentioned now the thermal magnons. So what does it mean? So here we need to distinguish thermal and coherent magnons. For data processing, usually we work with coherent magnons. So it means that there is some system, there is magnetization. We apply coherent field at 10 gigahertz frequency. We excite precession, spin wave propagates, phase is defined, clearly defined. There are many questions about quantum dephasing and so on. So principally, our lifetime is shorter. So our wave will keep most likely phase, unless you have some complicated multi-magnon scattering mechanism. If it's just linear system, a magnon will keep its phase until it dies. So lifetime is more or less defining everything. And this is a coherent magnons. But in addition, there are thermal magnons. Where are they coming from? That in each solid body there are thermal fluctuation of crystal lattice. Yeah, and if spin-orbit interaction is non-zero, then these vibrations of lattice, which are phonons, thermal phonons, which are also described by Bose-Einstein statistic, will be coupled to magnonic system. And as I said, if you wait long enough, there will be equilibrium between magnon and phonon. So it means that as soon as your temperature is non-zero or kind of small, not very small, then you will have some population also of exchange magnons. And these magnons are excited in the whole spectrum. So coherent magnons really depends how your antenna works. So you cannot excite very short wavelengths or very large K. It depends which frequency you can apply. So it's easy to apply up to 70 gigahertz. Yeah, it's a bit hard to apply up to 150 gigahertz. And if you want to go to terahertz range, you need another technique. It's all methodology completely different. Life is getting very tricky. So thermal magnons, as opposite, they are always in the system and they always exist for all modes. Up to the edge of first Brillouin zone, 7 terahertz, but also higher branches. Therefore, as soon as you have in the system your phonons, you will have also thermal magnons. And that's very important. And that's actually how Felix Bloch introduced magnon, 1929, if I remember right. He was describing as a variation of magnetization, which people could measure as a function of temperature for magnetic materials, obviously at low temperature. And they have found that the standard approach, where you just take Boltzmann statistics and plug in potential energy minus MB, that model does not describe behavior of magnetization on temperature at low temperatures. And he started to think what is going on, and that's how he introduced this flip of spin, which he named magnon. So that's how magnon was discovered. And it was done particularly in order to describe magnetization precession. So if you have static magnetization as a function of temperature. So what you need to do here, you need to introduce this number of magnons, where you integrate with f, its density of states, times this Bose-Einstein statistics. You integrate over all k, then if you will use some uniform density of states, simply volume of your material divided by 2 pi to the power of 3. And again, you consider equilibrium, mu equals 0, then this integral you will get this one. You simply plugged in Bose-Einstein statistic inside, and after integration, you will get this famous law t to the power 3 over 2. And and this principally is a famous law of Bloch. And here I should say, you can also check it in Grevich-Melkov book, is that it also works only for some materials. Although it's so advanced. For example, it does not work for yttrium iron garnet because, as we already discussed, so this formula more or less obtained taking into account only these magnons, but all these magnons also influence magnetization. Therefore, there is a deviation from T3 over 2 low for experimental measurements of saturation magnetization for YIG. So there are other mechanisms why there is might be a disagreement between this law and this formula. But for some other materials, it works perfectly. So that's so much about thermal magnons and magnon in general. Other questions? No? Good. Then very last slide, magnon relaxation. So here I just want to give you a taste. In reality, magnon relaxation, it's a big question. And first of all, we need to take into account relaxation magnon-phonon interaction, and there are different mechanisms. There is some people usually use so-called Kosuya-Lekrov mechanism, but Lvov, Zakharov, I think, have another opinion that that's not always work, let's say. So that's one story, big one, magnon-phonon interaction. Another story, when magnons interact with phonon directly. Another big story is metals, when you have free electrons. So what we see is that when you take isolator, like YIG or so, and then you switch to metal, where you have free electrons, there is also a relaxation mechanism for magnons because they interact with free electrons, and damping immediately 100 times higher. Therefore, metals, it's a second story. But here I would like to focus only on that magnon relaxation processes when energy from magnon stays within magnonic system, when it doesn't go to phononic system or any other system. And there are also a set of mechanisms responsible for this. And the first one is so-called linear or elastic scattering process, like it's shown here. And we have, the idea is very simple. You have magnons with energy 1, so with some frequency, with momentum 1, with some momentum, then it interacts with inhomogeneity. It can be static inhomogeneity, so it should not be phonon. Also, it can be defect. It can be the surface defect or any other, something which doesn't have energy but can change your momentum. Afterwards, there is an elastic scattering. Elastic means with the change in the energy, but you will get another momentum here, P2, like it's shown. And afterwards, so this is such a scattering mechanism where you keep energy, so the new magnon will have the same frequency, but another energy. And this is a very powerful mechanism, very important. So even in high quality yttrium iron garnet samples, like very rough estimation tells you that half of the losses of the energy, so if you excited some magnon of uniform precession, half of energy goes to other magnons, and half goes directly to phonons. Then, of course, from this magnons, it also goes to phonons after some time. But the just rough estimation, the two-magnon scattering is very important. Also, you need to distinguish two-magnon scattering in the volume and at the surface. Yeah. So also for thin films of micron thickness of YIG, usually also people roughly can estimate that half of the scattering happens at surface, half in the volume. But you need to keep this in mind. For example, when you go to fancy sphere, where volume is large compared to surface, then usually damping is smaller. When you go to very thin nanometer thick YIG, then surface plays more role, and that might be one of the reasons why damping increases compared to micron thick YIG. But there are nonlinear processes, and here there is 3-magnon decay and 3-magnon confluence. What does it mean? 3-magnon decay, one magnon with energy 1 P1 scatters into two magnons with other energies, E2, E3, and other momentum. What you need to, of course, to satisfy in this multi-magnon scattering process is energy and momentum. So energy, so it means that E2 plus E3 should be equal to E1, and the same for momentum, but for momentum, of course, it should be vector. Yeah, P2 plus P3 vectors should be equal P1 vector. And similar process is for 3-magnon confluence. The good point is that you can switch it on and off in practical life. For example, if you work with thick YIG, like classical micron thick YIG, then you clearly know where is your FMR frequency. Maybe I even will show you. You usually excite magnon originally here, and then it scatters to half, in the easiest case, just half frequency, here closer to the bottom. And it's interesting that if you will decrease this frequency, so you see here it's a bit more than 4 gigahertz, but if you would go around, I think a bit below 4 gigahertz, if I remember right, then you are allowed to get this energy and momentum conservation. So it means that magnons can jump here. If you go to this frequency or higher, half frequency, so and you excite something here, half frequency will be always below the spectrum. So it means that you simply have no magnon with half frequency where you can scatter. And in such a way, simply by tuning the frequency of field, so usually with field you tune the frequency, you can have a situation when you have allowed 3-magnon splitting or you have forbidden. And this is very good because the 3-magnon splitting, it has very small threshold, so even at minus 20 dBm or so, you already see damping, parasitic effect. And it pretty often creates problems for your measurements. Therefore, what people do, just increase a bit field, and then 3-magnon splitting is forbidden, and so on. Of course, keep in mind that this spectrum, it goes down to omega h frequency only for thick YIG. If you have a very thin sample, this dipolar part doesn't go bottom, so then it will be just such a small deviation, and then principally 3-magnon splitting of this type can be suppressed. But that what I present is very general, because numerically, if we, for example, simulated another mechanism, when you excited something here and you scatter to half frequency anyway. Therefore, principally, any scattering is possible. Also, confluence, if you will excite two magnon here, you can confluence it there. So you need to check in each concrete system. It all strongly depends on ellipticity, on the magnetization direction, and so on. Maybe at the very last lecture, we will discuss this a bit more. There was a question from David last time about two-magnon scattering, how it happens, yeah? How we can conserve energy, so to keep energy and to change momentum. Where do we have these magnons? And here's the answer. You see that we have many, many modes in the system, and its direction. So the point is that here this dispersion is shown only for waves propagating along and perpendicular to the applied magnetic field. In between you have all other angles, which we will discuss today. So it means that you already have here many thickness mode, and you already here have can satisfy two-magnon scattering. So it means you excite here, and then all modes at the same frequency can be populated due to two magnon scattering. And usually the most long-living magnons generated by two magnon scattering are sitting here close to this minimum because they have group velocity close to zero, you see. It means that radiation losses are small. And besides, because of their small wavelengths, they also don't feel inhomogeneities at surface and so strongly. Therefore, pretty often, when you excite something, yeah, your energy at the end of the day lives here into so-called dipolar exchange spin waves. My PhD thesis was about its theoretical description, and just last conference, Tuno and Dessau from Delft has shown they use this new technique with envy cells where they can detect very short wavelength spin wave. And he has shown picture where his simple Yick film was full of very, very short wavelengths, particularly these wavelengths magnons. And I was really happy because we knew that these magnons exist when I did PhD in 2008, but we didn't have technique to see them. And now I was really surprised that I see in his presentation, these are that magnets which are more or less staying in my PhD, but he could directly map them, and they really propagate in all directions, such chaotic. And these are these magnets which to my understanding, these are these magnets excited by two magnon scattering effect. Good. So then we discuss three magnon scattering. Main point that you can switch them on or off because of conservation energy and momentum, but even more important for our business is four magnon scattering. The point is that in four magnon scattering you can have it always, because in terms of energy and momentum conservation, of course you have to have E1 plus E2 equal E3 plus E4, the same for momentum, but with vectors, and this can be satisfied practically always, because you can scatter magnons themselves. So if you have two magnons located in the same practically energy and momentum, they can scatter in the same magnons here, or principally you can always find 2 points in the spectrum where you can scatter your magnons. The good point that threshold, or let's say this mechanism is getting more pronounced for higher applied microwave powers. So it means that if you work in our simplest experiment, just to give you some rough estimation, 0 dBm, most likely there will be no four magnon scattering, you don't see it. But if you will go to 10 dBm, so 10 milliwatt, you already will get scattering. And then it's getting stronger. Therefore, it's at macro scale. Yeah, at nano scale, it all depends how large your antenna and how good is characteristic impedance matched, and so on and so on. So it's all a bit more tricky business. But for us, it's just important to learn that there is this four magnon scattering mechanism. So I think I'm done with this lecture. Other questions or comments?